So this video is, the purpose is as a help session for your homework due over chapter 11, specifically in converting decimal numbers, which are base 10 numbers, into IEEE 754 single precision representation. So as an example, I've got this number here, which is a decimal number form, negative 19.77, which is a floating point number, and we want to take that number and we want to convert into the 32-bit IEEE 754 single precision representation. Okay, so to do that we need three parts. We need the sign bit, which is indicated by, coming from the sign and number, and if it's negative then the sign bit would be 1. If it's positive the sign bit would be 0. So we can put that number down right away because that's the very beginning of our 754 representation. So we'll do that. Get my pencil back here. Here we go. So that's a 1 in the sign bit field. And then the next numbers are the exponent, which are 8 bits long, and then the mantissa, or the fractional part, which is the 23 bits long. Okay, so to do those rest of those parts, we need to go back to our number here on the left, the negative 19.77, and we're going to take the first part here, the 19 part, so we've already accounted for the negative sign, so we don't need to do that again. We just look at the 19 on the left of the decimal point, and we're going to translate that into binary. Okay, so to do that, you take the number 19 and you divide it by the base each time until you hit 0. So we have 1, 9. We're going to divide that by 2. That's just the base in binary. The base is 2. And maybe I'll switch to this tool because the other one's kind of clunky. And that's going to give you a quotient of 9. And the remainder, make a new column, the remainder here will be 1, right? I'll put an R above that. So you know these are the really important numbers that you need to pay attention to. Okay, so then we're going to bring down that 9 number down here, and then we're going to divide that again by the base, and that 2 goes into 9 4 times with the remainder of 1 again. Okay, and we just keep doing that. So now I'm going to bring down my 4, the whole number portion. So 4 divided by 2 is 2, and the remainder is 0 in this case because it goes in exactly. And then we have, bring down the 2, so 2 divided by the base is 1 exactly, and the remainder is 0. Now I'm going to bring down the 1. So 1 divided by 2 is, well, 2 goes into 1 no times. I mean, there's no whole number. It's it has a remainder of 1. 2 goes into 1 0 times with a remainder of 1. Okay? And when you hit 0, you could bring it down, but it's just going to give you 0, 0, 0. So anything, 0 divided by 2 is just another 0 anyway. So we can stop when we hit that 0. Okay? So we stop right here and we have our number 10011. So that's right, you read from bottom to top. So make sure you know that you're reading from bottom to top for the whole number portion. Okay? So we'll put that over here. Let's see. About about right here. So we've got our left side figured out. 10011, and that's 19. You can verify that because the first number is to the 0, the second number is to the 1, so that's 3. To the 2, 2 to the 3, and then 2 to the 4. And 2 to the 4 is 16, and I said those two are 3, so that's 19. So that verifies the left side. Now remember your decimal point, you have to put that in. So let's put our decimal point in here. Put a decimal point in. Dot here. That's important. Now we have the right side. We need to translate the 0.77. So to do that, it's actually a different method because this is on the right side of the decimal point. We're actually going to take that number and we're going to convert it to binary by multiplying by the base instead of dividing by the base. Okay, so we'll start out with 0.77 times 2, and that's going to be 1.54. Okay, so with this now, the 1.54, you have the whole number part and the decimal point part. So this is a difference. So this whole number part, that's the most important part. That's going to be your bit that you're going to use as part of your fractional part. So I'll put a little b there to remind us that this is the field we have to be concerned about. And then the 0.54, that's what I'm going to keep using to multiply by the base. So I just keep using the decimal portion. I'm going to have quite a few numbers here, so I'm going to try to squish them in. And so that's going to be 1.08, and then I just keep going. So I have the 0.08 that I'm going to take and move down. So I'm just multiplying that fractional part, 08, times 2, and that's going to be, in this case, 0.16. Okay, then I'm going to move the 0.16 and bring that down. Got quite a few of these because we have 23 bits total. So 1, 2, 3, 4. So I'm going to need 19 of these. 1, 6. And just keep doubling this. Basically, is what I'm doing. Is I'm just going to double these each time. But I want to go slow so you can see exactly where all the numbers are coming from. And so I'm going to take my 0.32 now. And keep doing that. Times 2, and I keep going until either I get a 0.00 or I run out of bits. And so I'm still not at the 0 mark, so I might end up running out of bits here. So this one's 64. Bring that down. Times 2. So that's 1.28 now. So just take the decimal portion, the 0.28, double that. That's going to be 0.56. Double that. is 1.12. I'm just going to take the 0.12, double that, 0.24, then 0.24 times 2, 0.48, 0.48 times 2, whoops, times 2, 0.96, keep going, 0.96 times 2 equals 1.92, and just take the 0.92 part, 0.92 times 2 is 1.84, just take the 0.84 part, 0.84 times 2, 1.68, the 0.68 part, 68 times 2 is 1.36, take the 0.36 part, 0.36 times, 36 times 2, let's get this over a little bit, equals 0.72. Now 0.72 times 2 is 1.44. Just take the 0.44 part, 0.44 times 2, move that over a bit, equals 0.88. And see, how many do we have now? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. One more. 0.88 times 2 is 1.76. Okay, so in this case, we're going to read down. So our direction will be downwards. And we're only interested in the whole number parts. Okay, those are the only ones we're interested in. So that's what I'm going to use to put on the right side of this decimal point over here. So I'm going to put those in. So I'll have my complete 19.77 represented in binary. So I have 1, 1, and then I have 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1. Keep clicking on the wrong spot. Lost my place. See, I did 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1. Keep going with the ones. 1. Then another one and another one. So we have the 4 ones. Then we have 0, 1, 0, 1. Okay. Finally. So I've got my number here. And I need to convert this to scientific notation. That's the next step. So I'm going to take this number and just move over the decimal point. That's basically what I'm doing, got to move this decimal point over 4 places. 1, 2, 3, 4. So I have 1. I'm going to put my dot here, dot, so that you can easily see the dot. Okay. And then the rest of the number. So 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1. Stretch that out. And if you count that all up, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Ha! There's our fractional part of our single precision representation, right? Remember, the fractional part is 23 bits long. So I'll just put a little reminder here. So this is part, the F part, fractional part. Is 23 bits long. And what did I do to get that? I moved over the decimal place 4 places. So this number is actually times 2 to the 4. Okay? And that 4 is very important because now what I have to do is I have to take this part and convert the exponent part, so specifically this part, add it to the bias, and in 32-bit representation the bias is always 127. Okay, so that's on the slides. That's the convention, and it's got 8 bits, so you take that to the 8, divide by 2, subtract 1, you get the 127. So I need to add that bias in, okay? So I need to add plus the standard bias 127, and that's going to give us 131. Okay, and that number 131 I need to convert to binary. So you can do the same technique that I did over here with the 19, the whole number, and divide it by 2 each time. Okay, and you'll get the following binary number. You'll get, converting 131 to binary, you can use the same method, divide 131 by 2 until you hit 0, and you'll get 1, 0, 0, 0, 0, 0, 1, 1, which is the same as this is 3, basically, and this is 128. Okay, so that's 128 plus 3, which is 131. Because this is 2 to the 0, this is 2 to the 1, to 2 through 3, to the 4, to the 5, to the 6, and to the 7. So that's a 1, so that's 128. This is 3, so 128 plus 3 is 131. Okay, and this one is the exponent field, so that number is actually ready to go. And that is what's actually next in the single precision representation. So this is the exponent field. That goes in there. So that would be right next to the sign bit. So remember, this was the sign bit. And now this one's going to be the exponential, following directly right after the sign bit. 1, 2, 0, 0, 0, 0, 0, 1, 1. So that should be 8 bits, right? 1, 2, 3, 4, 5, 6, 7, 8. And then we have our really long fractional thing. That's what follows the exponential field. Okay, so that's this one here. This huge long number, which I'm just going to simply copy paste. Hopefully this works. This is the 23 bits long. And copy this. Just put it right next to it. Okay? Let's make sure 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay, that's the fractional part. Yep. Or F in the slides is shown as F. That's the is the 23 bits long. So that's your answer basically. You just have this entire thing, which is 32 bits, right? Because that section we just put in is 23, and then the exponent part is 8 bits, so that is 31, and the sign bit is 32. So the whole thing is 32-bit number, which I'm showing you on the screen as the answer to negative 19.77. So I'm going to box it to show you that this would be the answer, except that I don't want any fill. There we go. There's your 32-bit IEEE 754 single precision representation of negative 19.77.